Okay, this is gonna this will be the second to the last recording of this. All right. So here you go. We've got these two things here. Gosh dang! I wish I'd remembered my cat. The whole. Well, there it is. 8.1 times 3. So you go to 24.5. Now this is in meters per second squared. Okay, because remember the meters here wipes out that radius because this is unitless. That's the way we handle it. All right, so what this means is this is speeding up. Now, I want you to look at this. Since this thing was speeding up, all right, since this helicopter blade right here, and then it moves over to here, was speeding up. So right here, we calculated that its speed was, what, 132 or whatever that was, that 3 times 40.8, 122 meters per second right here. Now, there's also, what did we learn last semester, or for the last exam? If this is going 122 meters per second right here at this point, it's also got a tangent that at that point it's got a tangential acceleration going towards the center. Okay, and if the r is 3 meters per second, then the tangential acceleration at that moment is equal to 122 squared over 3 meters, which is equal to v squared over r. Well, we know that v is equal to r times omega, so you've got a new equation for AC, because if I square that, I get r squared omega squared over r, because I'm squaring this guy. That r cancels that, and so you get r times omega squared. And then the total acceleration, so let me figure out what that is real fast. Then the total acceleration of this thing, so let me figure out what AC is. What are you doing? Let me figure out what, oh, I'm after the calculator. Oh, I hit my notes instead of the calculator. All right, so here we go. So we've got 122 squared divided by 3. Huge! Look at the size of that tangential acceleration. 4,990, about 4994. We could almost, let's just call it 5,000. All right, let's just call it 5,000. So the tangential acceleration is equal, or the centrifugal acceleration is equal to 5,000 meters per second squared, and then the total acceleration of this thing, because we also have this 24.5 meters, the total acceleration of this thing would be equal to the AC squared, because they are perpendicular to each other, plus AT squared, whatever that comes out to be. I'm not going to bore you with that calculation. All right, so now, real quickly, this works just like linear, angular. Linear, what did we say? X equals the average velocity times time, where the average velocity is equal to v final plus v initial divided by 2. We also know that v final is equal to v naught plus at, because we know that a is equal to v final minus v initial divided by t, if it's a constant acceleration. And we know that x is equal to x naught plus v naught t plus 1/2 at squared, And we know that V final t is equal to V final squared plus 2a times x final minus x initial, or minus, depending on if it's slowing down or speeding up. Same thing over here. Theta is equal to the average angular speed times the time. The average angular speed is equal to omega final plus omega initial divided by 2. V final is equal to, or omega final is equal to omega naught plus alpha times t, or minus if it's slowing down. Alpha is equal to omega final minus omega initial over t. And same thing here. Theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. And omega final squared is equal to omega naught squared plus 2 alpha times theta final minus theta initial. Same thing. There you go. So this is one-dimensional kinematics. This is angular kinematics. And we kind of put the two together in Chapter 9. So on the next video, I'm going to do 2 practice problems and then call it a day. All right?